Hello everyone, this is our final presentation on the impact of fluid properties on consumer bottle design by Lauren Rogers, Paige Guidry, and myself, Conchordia. So why is fluid dynamics relevant to bottle design? Bottle design can change depending on the use. For example, you have your consumer beverages like water, milk, anything that you can consume like soda. Uh, the shape of the beverage bottle can influence how the liquid dispenses, considering factors like carbonation and serving size. Your container for yogurt might be different than something like water because of the viscosity being different, and you want your exit velocity to be slower as well for more viscous um, beverages. So, and then you have your consumer items such as shampoo bottles, skincare items, dish soap, where you want to emphasize the importance of viscosity, so you can have a controlled pour out of the bottle. And then you have your chemicals and oils where you don't want any turbulent flow coming out of the bottle when handling toxic chemicals or oils such as, motor oil or industrial oils. And then you have your quick drainage applications. There are only a few examples I could think of, but if you've seen refueling in motorsports where every second counts, applications such as that can be important in bottle design. And then one of the main things we wanted to emphasize within consumer beverages is user experience, such as the rate of pour, exit velocity of the drinks out of the bottle, um, and the diameter of the opening. If you've ever drank out of a Nalgene bottle, you know that you are more likely to spill all over yourself than a bottle with a smaller opening, such as like a Camelback. Um, so you also have spill prevention. If you ever tried to pour any liquid out of a bottle quickly, you get a glug glug effect, which is basically when air goes in to the bottle to equalize the low pressure inside the bottle as the liquid is draining out. You can install an anti-glug system where you can control the liquid coming out while allowing space for air to come in without having any turbulent flow coming out of the bottle. And then you have your specialty applications where controlled flow is uh, absolutely critical. Um, in medicinal purposes and chemical purposes, where even the smallest drop can make a big difference. So why is fluid dynamics relevant? So there have been studies and research done on this topic. In this one, they've done 3D CFD simulations on bottle emptying processes, and they were able to get some data out of it. They varied diameter and temperature for the first study on the left. I don't know why they didn't keep the same volume while changing the diameters, but obviously the ones with the larger diameter had faster emptying times. But that's not always a good thing in consumer beverage design unless your main goal is to empty the bottle as fast as possible. Um, they tested angle and fully inverted flows. On the right hand side, they tested fully inverted flows, where on the first bottle the diameter was less than 4 millimeters, and because of the surface tension effects, the bottle had no flow going out of it. And then in the middle one, you had oscillatory flow for your diameters under 16 millimeters to 6 millimeters. So basically, what that means is that the liquid and the air took turns exiting and entering the bottle. So it wasn't like one continuous exchange. And then for the third bottle design, you had a diameter of over 20 millimeters, and that was considered counterflow, where the air enters in to equalize the pressure, um, and the liquid goes out, and they're both simultaneous processes, and it's just one continuous movement, unlike the oscillatory flow. Another study that was done on this topic was a Japanese study where they took three different beverage size diameters, each of them being 5 millimeters bigger or smaller than the other. And they considered all consumer aspects to identify the best bottle design based on that opening diameter. So things such as, does it flow easily out of the bottle? Is the flow volume through the opening large? Does it feel comfortable in the throat? Can I incline it easily? Stuff like that. Um, a lot of these aspects are based on feel, so nothing like super quantitative. That's not to say the 33 millimeter is the best overall for any beverage. This is just the sizes that they picked. Um, and I doubt that, you know, there's one size that is best for all beverages. In this study, they used green tea and another carbonated soda. So they compared the two, and between the two, you know, they both turned out to have 33 millimeters as the best opening size. To wrap up the background on this topic, I wanted to talk about the glug glug effect and ways that that effect have been counteracted. Um, Basically, the glug glug effect is when the air goes into the bottle to equalize the pressure as the fluid is coming out. We talked about it in the previous slides, I believe, and um, that creates some sort of turbulence as the fluid comes out, and it can lead to like spilling all over the place, and just overall user unfriendliness, I guess. Um, One example of the designs that have been made to counteract that. On the right side, you can see for motor oil. If you've ever put motor oil in your car, you've probably used a bottle like this. At least I hope you have, because your car needs oil. Um, when the spout is on the top, the opening, as the motor oil comes out, there's space for air to go in, so you won't spill oil all over your engine bay, um, because you know you're making room for the air to go in to equalize that pressure. In the middle, you can see if you have the spot on the bottom, there's no space for that air to go in, so it's basically just going to force its way in and create that turbulence where you know you'll have oil all over the place because you can't have a controlled flow. And same with the first picture, you know, it's the same idea. Um, there have been some designs uh, that have been trademarked, such as a SafePort design. A company in the UK designed this where they allow air to go in even at 100% full, and allow the liquid to go out without having any glugging effect being present. So this can be useful in uh, large applications, you know, handling oils or chemicals where you need controlled flow. I was able to do a quick demo on the glugging effect using a motor oil bottle, one with the opening on the top and the other with the opening on the bottom. I had initially made a fixture at 30 degrees so that we could compare both pours to see which one got the glugging, but then realized the 30-degree angle was too steep for both of them because the oil would cover the opening completely, so the air would have to force its way in anyways. And then I realized people just don't go directly at 30 degrees. You know, they do a controlled pour. So that's what I did. So the fixture went to waste. And it was a pain to get the oil back in after each attempt. So I will show you the pour with the opening on the top. You can see that there's enough space for air to go in without any glugging effect. And the second video with the opening on the bottom, even with me going very slow, you'll get that glugging because there's not really any space for the air to go through to prevent that glugging effect.
In order to parameterize our system, we need a governing equation to calculate the flow coming out of any consumer bottle we're evaluating. And in this case, we can use our old friend Navier-Stokes. So we can see, as listed on the slide, a few things that we can consider just with this one equation. There's three main things to consider: the fluid, the bottle geometry, and then the user, so how that bottle is being manipulated. So the fluid, we have listed some parameters on the screen are density, viscosity, and surface tension, all of which can be accounted for within this equation. The impacts of the bottle geometry, we will see those through applied differential pressure. So if you have a change in diameter or any sort of radii or fillets, you can apply a pressure drop to represent those. Finally, when it comes to the user, depending on what type of bottle you're doing, such as a water bottle, we see the impact of that through gravity. So as you're tilting containers different ways, we'll see different forces of gravity. One of the first issues our team discussed when it comes to consumer bottle design is overcoming surface tension and viscosity. Surface tension you might have experienced if you've ever taken a glass jar of any type of sauce and had to really shake it and slam it to try to get it to come out. We can see through the equation on the screen that we're trying to overcome capillary pressure here. So for a given fluid, it has some value of surface tension that is a function of the perimeter of that fluid on the bottle. So the bottle needs to be sized such that the force of gravity acting on that fluid when you invert it is greater than the force of surface tension resistance. So you can see with the example of the photo I took there that the power of surface tension in my conditioner bottle is stronger than the force of gravity. Once your flow starts, you then have the resistance of flow through viscosity. So I have a simple equation demonstrated on the right-hand side for flow going down an inclined plane. So this shows us very simply how flow decreases with increased viscosity. You might have seen this if you've ever taken a honey bottle and you flipped it upside down and it takes a super long time to drip to the bottom to be able to squeeze out. As Kunj mentioned earlier, we have had the shared experience of going to drink from a largemouth Nalgene bottle and pouring it all over our face. So our motivation for our study was to see how we could mitigate that, what the causes were, and potential redesigns for future water bottle designs. So our initial guess was that it was due to the glug glug effect or air slugs going up the water bottle as you're drinking from it. First, we tested the flow just coming directly out of the water bottle, as you can see here. Then, because I am prone to pouring water all over my face, I had bought a fancy little mouthpiece for my Nalgene, so we tested that to show the difference in flow. It's hard to see here, but there is a top element that allows air into the water bottle that causes this very smooth flow. Next, we wanted to test how effective the same idea would be if you didn't have that little air inlet, so I just took some black duct tape. And you can see immediately we do have that glugging effect when you don't have the air inlet to stabilize the flow. Finally, I took a different Nalgene brand water bottle that had a regular mouthpiece to see how the flow is differentiated. And you can see when the water bottle is very full that you still have that turbulent effect, the glug glug effect, that's causing an uneven flow, although that probably is manageable. So as we saw in that first video, our hypothesis that we were splashing our faces with water due to the glug glug effect was incorrect. You could see that no matter how fast we poured the water bottle, the flow was very smooth, but we saw that it was very wide. So in the case of an Nalgene bottle, we learned that the actual issue was due to the orifice size being broader than our mouths. So when we look at this black mouthpiece, it has two features that add value. First of which is on the bottom, that arc gives us an optimized orifice size to be ideal to drink from, both from a mouth perspective as well as a flow rate perspective. As soon as you add this orifice though, as we saw with the final video, you need some sort of hole in the top to allow an air inlet to allow for a steady flow. So we saw no matter how fast I tilted the water bottle with the mouthpiece in, it was effective due to this air inlet. So when we're designing future water bottles or beverage containers, that's something that needs to be accounted for if we want the most optimal experience, both our opening size as well as having some sort of air port. We can see applicability when it comes to other beverages other than just water bottles. If you look at the left-hand coffee cup lid, you probably have memories of traumatizing yourself if you go to drink from it and splash your mouth with scalding hot beverage. Whereas if you have a lid like it is on the right-hand side, the opening is enough that when you slowly tilt your coffee, it can allow that air to balance out and have a small stream without burning yourself. So as we go forward, we can look at different concepts as we're selecting our beverage containers to be more optimal of a drinking experience.
Through background research and a few experiments, this project allowed our team to have really great learnings about how fluid properties affect consumer bottle design. In summary, bottles are designed based on the content or the fluid contained inside the container, and companies are interested in designing and updating bottles in order to control the flow of the product inside the bottle, which in turn enhances the user experience. Such parameters that companies may adjust include the orifice size, neck angle, radii, and the angle of pour. We learned more about the glug glug effect, which we may experience as we pour liquid rapidly from a bottle. And it occurs as the air pressure inside the bottle is lowered and air at a higher pressure outside the bottle enters, forming a bubble or turbulent flow. And we were able to see a demonstration of this effect thanks to Kunj. Our goal was to study an existing product or products and evaluate their bottle design against the properties of the fluid inside the bottle. This experiment was simplified to a Nalgene bottle with water, and this bottle was selected for optimization due to its large orifice and issues that users experience from pouring from this bottle. In the previous slides, Lauren touched on the findings of the experiment with the Nalgene bottle, but in summary, we discovered that the orifice size and having an air opening plays a huge part in optimizing the flow out of the bottle. We believe that the experiment was effective. However, for even further learning, the scope of the experiment could have been extended to test a different container or a fluid with a different viscosity. Regardless, though, our learnings are applicable to consumer product design as a whole, and it really helped us to understand what must be thought of in designing such bottles. The bottle redesign market includes modifying the size, shape, material, and the branding of bottles to enhance their aesthetic appeal, user experience, and marketability. Various food and beverage companies such as Coca-Cola and PepsiCo currently lead in this sector by actively engaging in bottle redesigns to constantly align with rapidly changing consumer preferences. We've noted several bottle redesigns that have happened recently that focus on the ease of use. The bent neck of the made to origin or M2O water bottle design shown in the bottom left allows the users to transfer liquid with ease and without needing to tip the entire bottle over for a constant flow. Also shown is the Quaker Oats Easy Pour on the top right. Traditionally, the container has been made to have a large opening, and consumers would either have to carefully pour oatmeal to avoid overpouring the oats or use a measuring cup to scoop out the oatmeal. But adding this paper feature inside the container allows consumers the option to have either a large or a small opening by simply punching along either dotted line and thus making it easier to pour out of the container. Other bottle redesigns, such as the P&G Easy Squeeze and the updated Pepsi 2-liter design, address pain points for consumers by adding features to allow liquid to pour out easier. The Easy Squeeze, which is shown in the top left, is an inverted bottle that features a no flip cap. And the updated Pepsi bottle design shown in the bottom right features an enhanced grip point that is slimmer than the old bottle, and it allows consumers to grip and pour easier, just thus making it more manageable. The global bottle redesign service market is seeing several emerging trends. One such trend is the growing demand for sustainable and eco-friendly packaging, thus leading to the use of recyclable, biodegradable materials and reducing waste. As an example, Coca-Cola launched new versions of its plastic bottles featuring an attached cap, and it's shown here in the middle of the screen. This bottle is aimed to reduce waste and litter and make it easier to recycle the entire Coke bottle at once rather than having consumers discard of the caps separately. Additionally, Dr. Bronner's, which is a top-selling soap brand, has released a refill carton that reduces plastic use by 82% more than their traditional bottles. Another trend that we're seeing is focusing on minimalistic and innovative bottle designs to enhance shelf appeal and brand differentiation. We'll continue to see updated bottle designs in various industries such as food and beverage, pharmaceuticals, cosmetics, and household products.